Thanks for coming. So this is the third one of these observatory nights that I've introduced, and it's been bad weather every time. So I know I'm not meant to be, I'm meant to be scientific about this, but I think I'm a jinx. So maybe I shouldn't do the next one, right? So waiting for the, you don't have an image up here.
Yeah, I know.
I've got the image on the screen.
It was up before.
Sorry for this delay. I think technical support is on its way.
It's not there.
It's still a beautiful night.
There it is.
There we go. All right.
Well done.
So do you recognize this image?
Yes.
Yeah, it's very famous. So this is from the Event Horizon Telescope. It's the first picture of a black hole. It's in the galaxy M87. So the CFA role in the Event Horizon Telescope is quite large, as some of you may know. So the director, Shep Dolman, is from CFA. There are quite a few scientists and engineers from CFA. Shep gave an observatory night talk about a year ago, I think. And also the SMA, the sub-millimeter array, which is that CFA has a large share in, was part of the Event Horizon Telescope array. That's over there in Hawaii. So it was a very big deal, as you would have seen. So these are a bunch of the CFA scientists. This is Shep Dolman, the director in the middle, and a bunch of others, postdocs and grad students. So they're quite proud of themselves, deservedly. So so it was really big news. And for the younger people in the audience, I'll point out that these are newspapers. They're sort of like a web page that you print out, and then it's obsolete by the time you printed it out, and it doesn't fit in your pocket. So they used to be very popular, and they're still a status symbol, as you can see. So this is a sort of a bigger collection of the images that went around around the world. I mean, we thought it would be front page headlines around the world, and it was. I did work a bit on the publicity at the last minute. So another, besides getting on the front pages of newspapers, the memes were quite the rage. So I think this is the most vivid one. It does look like a glazed donut. And so if you zoom out, and then of course Lord of the Rings had to play its part. I actually like this variation, which is when you put on the glasses, you see. And then, I mean, there are a bunch of tweets. There are a bunch of tweets that sort of made fun of the fact that these beautiful artist impressions were much prettier, much more spectacular than the actual image, which is really quite unfair. They're funny, but it's a little bit unfair considering the technical achievement that they made. So this is a very nice visualization that shows. It starts with a Hubble Space Telescope pixel. So the sharpest image that Hubble could make would be like way out here somewhere. So then it zooms in to the Event Horizon Telescope image just to show you how incredibly sharp that image is. And I'll see if it plays. So it zooms in a long way. So I think this is a really cool demonstration of just how sharp that image is. It's really remarkable. So for people to say it was blurry or fuzzy, come on. Yeah. So maybe not as well known as the fact that Chandra also, there were actually two NASA observatories, NuSTAR and Chandra, that observed M87 simultaneously with the Event Horizon Telescope. So this, that's the Chandra image on the left. It's showing the Event Horizon Telescope from the very middle. So this is a much, much bigger field of view. So it shows a jet coming out from the black hole and a bunch of other stuff going on. So the field of view of these two images is very different. It's almost a million scale difference. So that really shows you how much of a zoom in you get from the Event Horizon Telescope. So this is a still larger Chandra view, showing the part expanded there. One thing of interest here was that this was a director's discretionary time. So there's a certain amount of time that the Chandra director, Belinda, has to devote to unusually interesting objects like variable stars, explosions in the sky, and then this observation, I guess there was no peer-reviewed time allocated to doing simultaneous observations. So astronomers come to Belinda and say, "Can you please observe this? Use some of your time," and that's what she did, and it was good. It was part of one of the papers from the EHT. So one thing to note, I think is important, is that astronomers look back in time when they look at images like this. I mean, this is 55 million light years away, so that means you're looking as it appeared 55 million years ago. And so if you look further at greater distances, you're looking further back in time. So astronomers like to say that they basically have telescopes as time machines, that they're looking back in time. So I'm going to use that, motivated by that thinking of looking back in time. That's how I'll introduce Belinda, and that is to start at the present and then go backwards. So she's here tonight to give a talk about Chandra's 20th anniversary of launch. And then 2 years ago, she granted time to observe M87 for the 2017 run of the EHT. And then 3 years before that, she became the director of the Chandra X-ray Center. So I'd just like to highlight that she became the director on April 20th, 2014. So for the people who are good at math, in 2 days' time, that's a 5-year anniversary as director of the Chandra X-ray Center. So that's quite nice. Yeah. So she's the first woman was female director of a Great Observatory. So the NASA Great Observatory is the Chandra, Hubble Space Telescope, and the Compton Gamma Ray Observatory. So that's quite an honor, I think. Just to go backwards in time further, so let me make sure I get this right. So Belinda started working on Chandra stuff in 1995, I think. Yeah, I won't put you on the spot. And then 1984 is when she came to CFA. 1984, yeah. And then going back, you did a postdoc at Arizona, University of Arizona, and then before that a PhD at University of Cambridge. And then going back even further than that, she, I think, Belinda told me that she was inspired to get into astronomy in the last 2 years of high school when she read this book by Fred Hoyle about cosmology. And then Belinda's comment about her motivation was that she said, "I was fascinated that we could even have any ideas about how the universe works just from observing from the Earth." So I think it's quite cool that here she is, the director of this major observatory that's in space that we use to learn about the universe. So thank you, Belinda.
Thank you, Peter. I'm just going to make sure this works before I start. Always takes a bit of time to wake up. Never mind, I'll just use the laptop. So, good evening, everyone. Welcome to our public night. It's wonderful to see so many of you here and that you've come to join us in celebrating 20 years of Chandra science. For myself, it continues to be an honor and a privilege to serve as director of the Chandra X-ray Center. NASA's Chandra is the world's premier X-ray observatory, not that I'm at all biased. With its uniquely high spatial resolution, it is an amazing, groundbreaking, highly successful mission which continues to deliver science, exciting and new science even, 20 years into its life, which we hope will go for at least another 10 years more. So watch this space. And that was the picture I was supposed to be showing, which you already saw from Peter. So Chandra is part of the fleet of NASA's Great Observatories, which I'm showing here. The first to launch was the Hubble Space Telescope in 1990. Actually, I do have a pointer on this at least. Yeah, so here's the Hubble Space Telescope. I'm also showing here a temperature scale, which gives you the temperature of the temperature of thermal material that's emitting in the waveband of each of these telescopes. So in Hubble, Hubble looks in visible light and ultraviolet light, as probably most of you know, since I know you're all astronomy junkies or whatever, fans. You probably know more about this than I do. So we're seeing things that are at the temperature that we see on Earth with Hubble, and also some that are somewhat higher. This is a Kelvin scale, so 10,000 degrees. It goes from about 1,000 to 10,000 degrees if you go into the ultraviolet. 0 is minus 273 Celsius, so remember that, roughly. And this is a wavelength scale. Now, the electromagnetic spectrum is really light, and of course, visible light is a very tiny part of that spectrum. And I'm showing here the whole range. This is just a schematic view. It's not accurate, but all the way from the gamma rays to the radio to show you the wavelength of the light, how much smaller it is at gamma rays. The second one that was launched was the Compton Gamma Ray Observatory. That was in 1991, and it observed for about 8 or 9 years before it was actually purposefully deorbited. It only had one gyro left, and it was actually in quite low orbit. It was slightly lower than the Hubble Space Telescope, so it actually needed to have its orbit boosted twice during its lifetime to make sure it stayed up there. So it was purposefully deorbited to make sure it didn't land on something, right? So in 2000, they brought it back down while it still had a gyro so they could control it. And the pieces that didn't burn up in the atmosphere landed in the Pacific Ocean, which some of you may remember. In 2008, a second gamma ray telescope was launched, and it's still operating today and doing a great job in the gamma rays. Chandra was launched in 1999 to look in the X-rays. So in between these two temperatures, gamma rays come from material that's 10 billion degrees of order of magnitude. And then in 2003, the Spitzer Space Telescope, which looks in the infrared, so the cooler material, more like 100 degrees. And between them, they actually allow us to look at celestial sources at multiple wavelengths at the same time if we need to. And many celestial sources do give us light from many parts of the spectrum. And so in order to understand them properly, we need to see that light. Otherwise, it would be like taking an elephant and saying, not being able to see, and just knowing what the tail looked like, right? So if you just had the optical light, or you just had the gamma ray light. You see the tail of the elephant, and how do you know what an elephant looks like just from the tail? You really have no clue. So you really need to say the whole wavelength range to understand the object you're looking at, in most cases. So that's the introduction to the Great Observatories. Chandra, as I said, looks in the X-rays, and I'm going to show you a movie of the launch. The sound on, because you won't be able to hear it properly. This was in July 1999 on the Shuttle Columbia. It was launched from Cape Canaveral in Florida. You're seeing the engines almost lighting up, and there it goes. This was at 12:30 in the morning. And I was there. I took my children down and my husband. We went down for a trip, a few-day trip, which was good because it actually didn't launch the first time. It was the 4th day before it launched. But you can see it lights up the sky like day for probably about 30 seconds before it's high enough that all the light isn't there. And the ground under your feet is shaking. So if any of you have ever been to a launch, you'll know what this feels like. If you haven't, I highly recommend it. It's really amazing to just see this and to realize how much power it takes to get something off the surface of Earth and send it into orbit. You're basically escaping from the Earth's gravity. It takes a lot of power. It's also amazing to think that we as humans are able to do this. And then the next, whoops, don't want to end it yet. The next slide shows the shuttle. When it was up there, it orbits upside down. And this is Chandra in the cargo bay. I should also note Columbia was the only shuttle with a cargo bay large enough to take Chandra up, because it's as big as a school bus. It's really huge. So the mission specialist, Katie Coleman, has sort of, I suppose, turned a crank to get it ready to launch. And it's pointing back down towards the Earth. And then I have a movie, oops, which shows her letting it go. Here we are. So she's looking out from where the astronauts are and watching it let go. And basically what it's doing is that she undid it or untethered it, and then the shuttle backed away very, very carefully. This is the first thing they did when they got up there, because Chandra had a lot of fuel, it had its own rocket, because it's going into a different orbit. So if anything had happened, it could have blown up the shuttle and they'd all have been gone. So they called it the bomb, and that was the first thing they did, was to let it go. So here it goes. I'll just let it. You'll get a better view as it turns, as the shuttle moves away. I think now it's a handheld camera, so don't get dizzy. Also, one other interesting piece of information is that Chandra actually the shuttle ended up about 8 miles lower than it was supposed to. There was some minor fuel leak in one of the engines. And so the control center, which was back here in Cambridge, which then took over the control of Chandra once the shuttle was far enough away, had to recalculate all the firings in order to get Chandra into its final orbit. So the initial orbit is the shuttle orbit, shown in green here. And over a period of 2 weeks, they fired the engines to increase the apogee and finally the perigee and get it into its final orbit here. But they were starting from a different point, so they had to redo all those calculations in a hurry so that they could start Chandra going to its final orbit, which they got to successfully. It goes about a third of the way to the moon. So here is the moon's orbit. This is a little moon here. And this is Chandra going around the Earth and the radiation belts schematically shown here, artist's impression, and then just showing the orbit here. We go through the radiation belts about every 63, the orbit is 63.5 hours, and we have to close the telescope down while we're in the radiation belts. That's for about 17 hours of that 63.5, because it moves faster when it's near the Earth, because that would be dangerous for our instruments. But the rest of the orbit, it's observing the sky, celestial sources. So it's pretty efficient from that point of view. So how do we make an X-ray image? What I'm showing here is how you make an optical image with a telescope. Now, we're all familiar with standing in front of a mirror. The light comes from us to the mirror and back so we can see ourselves. It's just reflected at 90 degrees. And our eyes do the focusing. If you have a telescope, you need a curved mirror to take parallel light from a distant celestial source and focus it down at a point here. So this is normal reflection. However, if you sent X-rays into that mirror, they go right through. And of course, we know that because when we go to the doctor and we've broken our arm, they use an X-ray machine to see inside your arm and see what's happened to your bone. So it wouldn't even see them. So how do we focus X-rays? We have to do it with grazing incidence. So here we have incoming X-rays from a celestial source, and we have these very, very smooth mirrors here, and each X-ray hits 2 mirrors and then goes down to the focal point in both directions. This is called grazing incidence reflection. On Chandra, the angle is about 1 to 2 degrees. And this means the mirror has to be incredibly smooth, and this was the biggest technological challenge in building Chandra, was to get the mirrors that smooth. Because not only are X-rays much shorter wavelength, and of course it has to be smooth enough that those photons aren't going to notice any blemishes, if you like, on the mirror, but also it's grazing incidence. So if you imagine yourself lying on your tummy in a grass, just on the grass at home or wherever, and you look at the grass in front of you, you can see every blade. Some of them are a little taller than others, right? You see all the details. If you stand up and look down, then you just see a green lawn, unless you're on my lawn, and then you see a lot of moss as well, but in general. So the point is that in order for that grass to look smooth at that angle, it would have to be cut really, really accurately. You'd have to plant it very close, etc., etc. So these mirrors are incredibly smooth in order to be able to focus X-rays. This shows you the light path through Chandra itself. So the X-rays are coming from a celestial source. The mirrors are at the front instead of at the back. And the instruments are down here, 10 meters away. And I'm showing a cutaway here so you can see what they actually look like. So you make a cylindrical mirror. So you catch all the light in the whole circle around. It's just cut away here so you can see that there are 6. And the highest energy X-rays come in at the smallest angle at 1 degree on these inner mirrors. And as you move out, there are slightly lower energy X-rays coming from each one. Also to note that there's a special shape for these cylindrical mirrors. These are paraboloids in surface, and these are hyperboloids. So these doubly reflected X-rays then go 10 meters onto the instruments that we put at the focal plane. All right, so that's a telescope. Why do we want to look at X-rays in the first place? What are we going to be seeing when we look in the X-rays? So X-rays come from the hottest and most violent places in the universe. I really love saying that. Makes it sound very exciting, which of course they are. But what are the hottest and most violent places? Well, stars. When stars are born, things are very hot and very violent. When they're middle-aged, like the sun, it's not particularly. If they're interacting, then you get a lot of X-rays. If they're merging, you get X-rays. And if they're dying, you get X-rays. So it's a bit like, birth, death, and getting married. They're all the most exciting parts of your life, right? Black holes. We just saw a black hole, the first image of a black hole. Any size of black hole accretes material because there's a lot of gravitational forces there. These are called active black holes. So they give us a lot of X-rays. Galaxies actually contain a lot of very hot gas that's shining in the X-rays because it's very hot. Even planets, which seem like fairly cool and normal places. We live on one after all. This is Jupiter, the optical picture of Jupiter, and this is a Chandra image of the aurorae in purple. There are actually X-rays coming from the aurora in Jupiter in the north and south poles. So in actual fact, most types of celestial sources do give us X-rays at some point during their life. I'm going to give you a tour today of a few of these kinds of sources. I can't talk about all of them, but I'll give you some idea of the kinds of things we see. So this is actually not a Chandra picture. This is a ROSAT picture. ROSAT was the previously highest resolution X-ray mission. This is looking at the Orion Nebula, which is a star-forming region, which is actually in the Orion constellation. Those of you who have telescopes or even looking with your eye can see it. It's below Orion's belt, in the middle of his dagger. And you can see it best if you look at the dagger and then avert your vision. Most of you probably know this better than I do, because you're all amateur astronomers and I never was. But you can see this little fuzzy thing in the middle of the dagger. And this is the Orion Nebula. So this is the X-ray emission from the Orion Nebula. We see 100 sources, and you can see in the middle it's completely washed out. They're all just blurred together. There are too many of them. The telescope can't resolve them anymore. But I'm going to merge into the Chandra image, and you can see why we love Chandra so much. We can now see all the stars, even these ones in the middle that are so bright that the edge of the point spread function makes it look big. It's much fainter, and you can see these little dots around it. You can actually resolve the stars right next to it. So we now have 1,400 stars in the middle of this star-forming region. Now, X-rays turn out to be a very good way of finding the youngest stars in star-forming regions, because if we look at these regions in the optical, on the infrared, there's a lot of gas and dust in our way, and we can't see them all. Whereas in the X-rays, because they look through all that gas and dust, we pinpoint the youngest stars. And they're very violent and unstable places because you've got gravity pulling the material together, forming this star in the core, The middle has just got dense enough for fusion to begin, and it's now sending out radiation, and that's pushing more of the material away. And so they're very hot and violent and unstable until they settle down. So Chandra is an excellent young star finder. We've studied quite a large number of star-forming regions in the solar vicinity in our galaxy and learned an awful lot more about how stars form in different regions from Chandra. So I'm now going to move from the birth of stars to the death of stars. Now, when a massive star runs out of fuel, so it's turned everything in its core into iron and can't go any further in terms of fusion, what happens is that it explodes, and I'll just tell you the story of that with this schematic here. So you have a giant star, there's no more radiation coming from the core, and radiation has been balancing the gravity. So now what happens is the gravity wins, and the core collapses very fast. And as a result, it sends shock waves through the outer parts of the star, and they expand, and it blows up in a big explosion. Our star, the Sun, will not do this. It's not a massive star. It's only it'll just gradually get old and big, but it won't blow up. But a massive star, 10 times the mass of the Sun or higher, will blow up. And what we end up with is a neutron star, so very dense material. It's mostly made up of neutrons. In a star that's about 10 kilometers across, and then a lot of material that's just expanding outwards and keeps going. So, did I say all of this? Oh yeah, a supernova, when it blows up like that, is brighter than the galaxy it's sitting in, and a galaxy has 100 billion stars in it. So can you even imagine being brighter than 100 billion stars and you're just one? It only lasts for a few hours or maybe a day or so, but they're very, very bright. Supernovae are also the primary way that the heavy elements are generated and distributed into the universe as a whole. So the universe is started as mostly hydrogen. We're not made of hydrogen. We're made of much heavier elements than that. The atoms in our body had to be made somewhere. And in fact, they were made in the center of a star, and they were blown out in a supernova remnant, and the remnant expanded, and eventually they came into the next generation of stars and made Earth and the Sun, and here we are. So we're actually made of starbursts. The atoms in our body were born in the core of a star like this one. Also an amazing thing to think about. So the supernova remnant that I'm showing here was the official first light picture, which was taken in August 1999. We knew it would be pretty because we'd seen it with Rosat, and it was kind of blurry compared with this, but still very pretty. So this was our official press release. It's a supernova remnant in the Cassiopeia constellation. The A means it's the brightest radio source as well in that constellation. It's 300 years old, and its size is about 29 light years. With this first picture, we found the stellar remnant, the central compact object, as it's called, which is the neutron star right here. Hadn't been seen before, again, because there's a lot of material in the way, and we needed the X-rays to see it. Now I'm going to fade into a much higher signal-to-noise picture. This took 12 days to get all this data, but as we add more photons, we just get nicer and nicer pictures. It's incredible. What we're seeing here is a lot of hot material. Because it's young, most of the material is still very hot, and it emits mostly in the X-rays. And in the blue here is what's called non-thermal emission. This is not shining in the X-rays because it's hot. It's shining because we have electrons that are very, very energetic. They have a lot of velocity, and they're moving along magnetic field lines and radiating what we call synchrotron radiation. So it's actually a new component of supernova remnants that was discovered by Chandra. So there's the same image, and this is the optical image, and you can see it's much less interesting in the optical. So only the coolest material in here is visible in the optical. Also note there's a lot of stars visible here that we don't see in the X-ray. So they're not stars in the supernova remnant. Some of them are between us and it, some of them are behind it. So they just get in the way of the view. We can also do a little bit of observing here in the room. For every photon that Chandra detects, we don't only get its position, we also get its energy and the time it arrived. So we count every single photon. And we can do that because we have way fewer photons than the optical telescopes get. But each one is very energetic. So we can also plot up a spectrum of all the photons in this image. And that's what I'm showing here. This is going from 0.5 by the looks of things to about 7 keV, which is almost the full band of Chandra. The shape of this just shows you the response of the instrument. But you can see these emission lines here from iron, calcium, argon, sulfur. So we can see that these elements are here. And if we look over here and color code, which this has done, the energy of the photons to a color here, you can see that, for example, the red photons are here. They're mostly made up of iron, it turns out. So this red here is iron. And in fact, iron was what was in the core of that star before it blew up. So what we see immediately from this is that the star blew inside out. So a lot of the material from the very core didn't all collapse. Some of it came out and it moved the fastest. And here it is on the outer parts of the expanding nebula. There's also a bit of a jet kind of emission here, which mostly seems to be silicon here, and you can't see it so well on this side. What do we do with supernova remnants? We understand how they explode, or we try to understand it from doing these observations. We find the neutron stars in the cores. We've found quite a few now. We can measure the expansion. This one actually has expanded a little bit over the 20 years. And as I just said, we discovered that the explosion is inside out. We also can get a 3D picture, if I can get this movie going, because we measure the velocities from these emission lines, and you can see what's at the front and what's at the back and what's at the sides. So you get some idea of what the three-dimensional structure looks like. Here's a montage of a few more supernova remnants. These two look very similar to the one I just showed you, to Cassia. This is Tycho, and this one has numbers for its name, so it's not very memorable from my point of view. But these two look very different. And the shape really depends not only on how the star explodes, which is also obviously part of it, but also what it's exploding into. So how much material the star let go before it blew up, or how much material was around it in the region where it was sitting all of its life. This one looks very, very complicated, for example. This is very famous. This is the Crab Nebula. It actually has the first ever discovered pulsar in it, which we now have seen in the X-rays. It's right here. And this actually was due to a supernova, but this is called a pulsar wind nebula. So this is non-thermal emission here. And I have a bigger picture. So in the X-rays, we're seeing non-thermal emission because the pulsar has magnetic fields. It's accelerating electrons, just as I described before, and it's producing synchrotron emission all around it. There's also a jet in this direction and in this direction. Now, the picture on the right is a very narrow band Hubble filter. So it actually does manage to see some of the same structure. And we took 7 pictures of this a while ago now, and it's been put into a movie that's repeating. So you can see that it actually changes in the time scale of a month. Okay? The jet actually moves. This is the pulsar here. You don't see it in the HST image. There's a standing wave here, but the emission around that ring is changing as a function of time. So we can actually see things vary on reasonable time scales in the X-rays, which is great. Okay, I'm going to move on to quasars, which are actually galaxies that have a supermassive black hole in their core. And that supermassive black hole is accreting material from the galaxy around it, and it's called an active galaxy. All galaxies have supermassive black holes, even the Milky Way. But the Milky Way supermassive black hole is not very active. Just every now and then it has a little outburst. But a quasar, we have very big outbursts for quite a long time. The supermassive black holes are at least 1 million times the mass of the Sun. They go up to 10 to the 10 times. They're in the nuclei of these galaxies. And this is an artist's impression of what it should look like. We have a black hole in the core. This is almost edge on, so you can't see the black hole. The accretion disk is very, very bright because the material gets incredibly hot trying to get in to the black hole. So it forms an accretion disk because it's moving around. And then beyond that, you have cooler material also trying to get down there, which blocks our view if you're looking edge on. You can't really see the black hole from this. If it was exactly edge on, you'd see very little of this light. So the view depends on the angle we're looking at it. And these are radio jets, which are present in pretty much all quasars, but in most cases they're not very bright. However, in this one here, I'm showing you the radio map of Cygnus A, which is a very big radio quasar. So this is just radio emission. The supermassive black hole is down in the core. And now you can see these very narrow jets. They're moving relativistically, very, very fast electrons going around the magnetic field. At some point, they impinge upon material here, either in the intergalactic medium or perhaps in the galaxy they're situated. You get these hot spots where that interaction is happening. And a lot of the plasma being ionized particles, just kind of moves out, slows down and moves out, and it generates these lobes, we call them, radio lobes. So this is a classic double lobe radio source with jets feeding it. So now I'm going to take a little bit of time to tell you the story of the first source we actually looked at before CASS-A. And this is a quasar. It's called PKS, which is Parkes for a radio telescope. So since you're all very intelligent people, you'll already have realized that it's a radio loud quasar. And this number tells you roughly where in the sky it is. So minus 75. Parkes is in Australia. So it's in the southern hemisphere. This was the point source we pointed to focus the telescope. So when you have a quasar, a supermassive black hole that's accreting, the amount of radiation and light that's coming out of that is brighter than the whole galaxy around it. And so if you move it a little bit of distance away, you don't see the galaxy at all anymore. You just see the core. You can't resolve it. So it's a point source. So it's perfect for focusing. This one is a redshift of 0.5, which is about 9 gigahertz away. However, this is what it looked like. There was a lot of consternation in the control room. I wasn't there. I'm glad. I probably would have had a heart attack. They saw these extra X-rays at the side, on the west side. And not only that, they seemed to be in a very particular place. And so apparently they were trying to figure out whether something could have got wrong. This was the first source we looked at. Has something gone wrong and launched? Did one of the mirrors get misaligned? Did something lie in the light path? They couldn't figure out a way to get something that looked like this. Aha, though, this is a radio loud quasar. It has a radio jet. In which direction is the radio jet pointing? It turns out right here. So in our first observation, we discovered strong, bright X-rays from the radio jet in this quasar. This was new discovery. We weren't expecting them to be anywhere near this bright, even if there were X-rays. And it opened a whole new field that Chandra has taken great advantage of. And we understand jets much better now because we can look at them multi-wavelength. X-rays, radio, we sometimes see them in the optical, though not in this particular source. This is a figure taken from one of the papers that was written about this source. It shows the radio data with the contours on top of it. You can see it's a pretty narrow jet. It's brighter here than anywhere else. And then it takes a bend here. There's probably some material there that's stopping and deflecting the stream of electrons and probably also slowing them down. This is the X-ray. The resolution isn't as good. The radio, as Peter already showed you, radio gets much better resolution than we can get, though this isn't as good as the M87 picture. So this is a point source, so we could still focus. And this is the jet. It's brightest where the radio is, but then it stops. So the electrons have been slowed down enough that they can no longer produce X-rays at this point. So we learned something right away. It's 9 arcseconds long, 250,000 light years at that redshift. So it's a pretty powerful jet. So now I'm going to move on to M87, which you've already seen today, which is one of our favorite sources for a number of reasons. It has this jet in the core. It's in the Virgo cluster, I should say. It's one of the brightest galaxies in the Virgo cluster. This is X-ray emission from around the galaxy. It has an X-ray core here, which I'll zoom in on. This is the picture that Peter showed you. So here's the jet in M87. And this is what it looks like in multiple multi-wavelengths. So this is the Chandra image. You see, you can actually see individual photons in X-ray data. It's amazing. This is the background level here. We don't get much background. This is this Hubble Space Telescope image, so it's very bright in the optical, and this is the radio image. And again, you can see there are hot spots along this jet. It's pretty narrow. There are bright areas. And by studying the relative amount of emission in the radio, the optical, and the X-ray, you can learn, in each of these hotspots, you can learn a lot about how jets work, and we have done since being able to study them in multiple wavebands. We also see the X-rays pretty much stop again where the jet starts to wiggle around and it's probably interacting with other material. Now we go down to the radio core here, and you know what I'm going to show you next. The image of the black hole in the core of M87. And we did look at it at the same time because some of the X-ray emission is probably coming from right down here. We can't see it coming from right down there, except we can see it very, very rapidly. So it's probably coming very close to the event horizon. So there'll be a lot more work on this source, I'm sure. Staying with supermassive black holes, I now want to talk about binary supermassive black holes. This was the first binary seen by Chandra. It was in a nearby galaxy called NGC 6240, which is shown in red in this image. You can see it's a bit of a mess. It doesn't look like a nice elliptical galaxy or even a nice spiral galaxy. It's got bits coming out all over the place. And what's happening is there are two spiral galaxies that have got too close together. They can't escape from one another, and they're in the process of merging. And when we looked at it in the X-rays, we see not just one, but two bright X-ray sources. So there are two active nuclei, two active supermassive black holes in the core of this galaxy. They're only about one kiloparsec, about 3,000 light years apart. So they're very close. The galaxy itself is probably about 10 kiloparsecs, which is about 30 light years across. So they're really in the core. Now, binary black holes like this will eventually merge as the galaxy finally settles down and becomes whatever it's going to be in the future. Those black holes will eventually merge. This has become a very hot topic in the last few years since LIGO has detected merging stellar mass black holes. They're much, much smaller than these, right? So they're tens of times the mass of the sun. This is at least 1 million times the mass of the sun. But basically it's the same physics, the same process. So they have seen merging stellar mass black holes in gravitational waves, as I'm sure many of you know. Merging supermassive black holes are not detectable by LIGO. They're too big. The gravitational waves have much longer wavelength. In order to see something like this merging in gravitational waves, we will need ESA's LISA satellite, which is scheduled to be launched in the early 2030s. So we've got a while to wait yet. That will place detectors in space so they can be much further apart and detect longer wavelength light. So those of us who are around in the 2030s can look forward to that. This is a movie made by our very talented public communications group at the CXC. Whoops. It is really a movie, honest. As to what, an artist's impression, if you like, of what happened to NGC 6240. So we had two perfectly fine spiral galaxies. They got too close, and they couldn't get away, so they're merging together. Now we've zoomed in, and we're seeing two accretion disks, 1, 2, with black holes in the center if you're close enough to see them. And they're orbiting around one another, and as time goes by, quite a lot of time, at least millions of years, they get closer and closer and faster in their motion, and eventually they're going to merge. And since we don't have LISA yet, there are the gravitational waves. So looking for binary supermassive black holes is another industry, if you like, of Chandras. There are multiple ways of finding them. You can find them in the optical, but you're not sure you've seen them until you actually see two supermassive black holes that are alight, that are active in the middle of the galaxies. So here, this is a Magellan image of two probably spiral galaxies, but the arms are all going the wrong direction. And there are two sources in blue from Chandra that are 60 light years apart. So this is a beginning of a merger. They're quite far apart, but they will eventually move together and merge. And then here's another one. This is Sloan Digital Sky Survey picture. In red, you can see the optical. It's still, messy galaxy, but not quite as messy as this. And the Chandra, in white and blue here is the Chandra image, which shows you two cores, two active nuclei. They're only 10 light years apart. So if we look at a sample of galaxies and find out how many are binaries and what their separations are, we can understand how frequently galaxies merge and how frequently supermassive black holes will merge. That will actually help us predict what LISA will see when it goes when it's launched and can see supermassive black holes merging. And also help us to understand about galaxy evolution. So that's what we do with those. So staying with gravitational wave astronomy, those of you who are following this will recognize LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. And there are two US facilities, one in Texas and the other in Washington. I keep getting these mixed up because Texas is supposed to be brown and Washington's supposed to be green, and yet apparently it's the opposite. I think I got it right this time because they actually labeled them. There's also one in Italy called Virgo, which will be relevant in a minute. Now, LIGO has been finding these merging black holes, and this is not a real image. This is a simulation of what they will do, and this allowed them to predict the signal that they would see with LIGO. And so they knew what they were seeing as soon as they saw that signal. It's basically, I wish I had the sound here. It's very, very fast. It's less than a second, and it goes whoop, like that. Something like that. You've probably heard it, some of you at least. We don't expect any electromagnetic emission, that is light, from merging black holes, because basically everything goes in because of the gravity. There's no light that escapes. So although we have looked, some of us have looked to follow up, some I don't think Chandra has, because we didn't expect to see anything. But some people have looked just in case we're wrong and there's light coming from them, but we haven't seen any yet. So they've found quite a number of these now over the last 3-4 years. However, 2 years ago, very exciting for the electromagnetic community, they saw their first merging neutron stars. So these are stars, as we already talked about at the beginning, are born when a massive star blows up and goes supernova. You end up with a neutron star. Now, to have merging neutron stars, you have to have two of them. So you have to have a binary star, a binary star is two stars. Both of them at some point have to go supernova and leave behind a neutron star. Now, usually the companion star doesn't get blown away when the star blows up because it's pretty small and it might get shaken around a bit, but usually you end up with a binary neutron star. And so eventually, as they lose energy over time, they will merge. So about 3 days before the solar eclipse in 2017, when most of us were on our way, it turns out, to Idaho, Sun Valley, Idaho, to a meeting that had been specially timed so we could see the solar eclipse, which is really neat. I hadn't seen one before. I recommend them. That was sort of an aside. So I was on a plane, I think, when this came in, or maybe I was leaving the next day. So they found merging neutron stars with a gravitational wave signal. This is much longer than for the black holes. It's much smaller. It's only 1 to 2 times the mass of the sun. So it's a bit of a longer signal. It's more like 2 seconds. So Fermi, the gamma ray satellite I told you about at the beginning, is always looking for gamma ray bursts of various kinds. So as soon as they saw this trigger, which came out a bit later, they looked back in their records, and yes, sure enough, they'd seen what's called a short gamma ray burst. This one was particularly faint, so they hadn't really noticed it, but it was detected significantly 2 seconds after the trigger at LIGO. So we're seeing faint gamma rays. Immediately, all these telescopes around the world with teams who were have been waiting for these merging neutron stars for years, turned their telescopes. They had to wait till it got to be dark in America, and north and south, actually mostly south. And they had to look from galaxy to galaxy within the error circle of where this gravitational wave source was, because it's not very well defined. Not even Fermi can give you a very good position, though it helped. But the third gravitational wave facility in Italy also helped, because it did not see this. So it wasn't visible to them. So that cut down the error. But anyway, they went from galaxy to galaxy looking for a source that wasn't supposed to be there. And eventually it was found. This is the optical picture from Hubble. In actual fact, it was a ground-based small telescope that found it. So you don't need Hubble to find these things. But to make a very pretty picture of the galaxy, you do need Hubble. So here is the source. It's in the outer part of a galaxy. This black ring circles where it is. 2 days after the trigger, we looked at it with Chandra. We had some programs in place that were ready in case there was a trigger from a neutron star merger. And so they switched on. They wanted to look earlier than they'd originally asked for, so we looked in 2 days and we saw nothing, which is a little depressing to begin with. This circle is the same size as this one, so there's nothing in here. There's one X-ray photon that's background just above. But they still wanted to look again. They knew more about it than me, so I said, okay. So a week later, there it was. We saw it. Now, both these observations are important, because if this had been a gamma ray burst pointing right at us, which is usually what we see, because those are the brightest ones, gamma ray bursts have jets. If you look down the jet, you see the emission incredibly brightly, because it's non-thermal, relativistic electrons, and it's beamed right down that beam, so very bright. This was faint, so it wasn't the normal short gamma ray burst. So Fermi had only seen a very faint signal. We saw nothing. However, a week later we saw something. So this tells us that the jet is not pointing at us, but it's pointing fairly close to the line of sight. As the jet moves away from the neutron stars, well, it continues, but as it grows, it actually expands. It isn't so narrowly collimated. So the solid angle it's filling gets bigger. So we started to see what they called, I think they called it a structured jet. We saw the outer part of the jet, which was not quite as relativistic as the core, but we began to see the X-rays from that. We observed it twice more, and then it went behind the Earth. And we couldn't observe it for 3 months. I should note the optical counterpart was tracked also until 2 weeks later when it went behind the Earth. And it had already faded by then. It was quite bright. It was blue to begin with. It turned red, and then it faded. So they wouldn't have been able to look at it anyway after that. The optical emissions coming from the material close to the neutron stars rather than from the jet. So we weren't able to look at it in the X-rays until December. During that time period, radio observations continued. They had not found it by the time it went behind the Earth, but it can observe during the day. So they actually did find it within a month or two, I can't remember exactly when, and tracked it. And then in December we joined them, and we found that it was 4 times brighter. And we then watched it about once a month for a while, and it was moving in track with the radio. So that tells us that we have synchrotron radiation, just as I just described, and we see radio emission as well as the X-ray. And this is the latest in terms of the models. We've continued to watch this source. I'm giving credit here, because this is not published yet, to the scientists who took the most recent data point. There's a lot of people involved in many of these data points. This is the schematic of the picture that we have. We have the neutron stars that merged here. We have the binary plane is shown down here. And these are the jets, which would have started out quite narrow. But when we first were looking at it, they broadened a bit, and we were looking down this outer part, which was mildly relativistic, whereas the jet core is ultra-relativistic. So looking over here, this is a light curve. So the X-ray flux is a function of time in days. This was our upper limit. And these were our 2 detections. Here's where it went behind the sun. And this was December when we saw it again. It was quite a bit brighter. This is a log scale, so it's a factor of 4. It went up again for a little while, then it turned over. So what these authors think is happening is, as it continues to broaden, it's interacting with the material around it, it's going further away and getting bigger. We're now looking down a much wider jet core once we get to this point here. And now it's just decaying because it's getting bigger with a power law slope, what we call, which is a slope of about -2, which is what they expect. So we're still looking at it. We're looking at it about every few months at this point. We should be able to see it. Probably, this was an upper limit here, so we probably can see it for another few months, I would say, before it's too faint for Chandra, or else we'd need to look at it for too long to make it worthwhile. We'll see. I'm sure I'll have people asking me to give them more time so they can just get one more point. We'll see how that goes. But we think we understand this quite well. LIGO is now operating again. It started a week or 2 ago. It's already found a couple of merging black holes. We're hoping that it'll find a neutron star soon. And then my last science topic is clusters of galaxies. So now we're changing tack completely. These are the largest gravitationally bound systems in the universe. They include 50 to 100 galaxies. And here I'm showing you the Perseus cluster in the optical. This is a movie thanks to my colleague Paul Nander in Europe. It's zooming out. This is the brightest cluster galaxy. It's called NGC 1275. It's really gorgeous. It has all these beautiful filaments coming out where stars are forming, etc. There's a lot of galaxies here in this cluster. Now I'm zooming from the optical to the X-ray. This is the hot X-ray gas. It fills all the space in between the stars. There's actually 10 times more X-ray gas in terms of mass than there is in all those galaxies and all those stars. 10 times more. We thought, when we first looked at these with Chandra, that they'd be pretty boring. They're big. They've been there a long time. The gas must be in some kind of equilibrium. We thought we were just going to measure how much there was, what temperature gradient, etc. But no, they're clearly not very boring or stable places. They've got these cold fronts, which are probably occurring because another cluster came a little close to it, and the gravitational force and torque from that just made everything swirl around. Just like if you have a glass of wine and you swirl it around to get the bouquet, right? It swirls around. That's what this gas is doing. On top of that, we have a supermassive black hole in this galaxy, NGC 1275. It's right there. You can see it's quite bright there in the X-rays. And it is sending out jets that they go for a while and then they stop. And so what that does is it pushes all the hot gas away. So you end up with a void. Here's one. Here's one, here's one, here's one, where the plasma from the radio jet has pushed away the X-ray gas. So you get no X-ray emission here. The X-ray gas is all gone. You've just got plasma in there that's giving you radio emission. And so what this is doing is telling you, it gives you a fossil record of all the outbursts from that supermassive black hole. Fossil, of course, in quotes, not really a fossil, but a record of all the outbursts. So this must have happened much earlier than this, because the void just keeps moving away from the supermassive black hole. And here's some younger ones. They're in a slightly different direction. So the supermassive black hole must have precessed, and it's sending jets in a slightly different direction. So they all look like this. All the clusters, they all have this structure. So they're really fun to study. This is another one where we can see the whole thing a bit better because it's further away. It has a name that tells you where it is in the sky. Here I'm showing the galaxies and stars in white. The X-ray gas is in blue, and you observers in the room will see that there actually isn't much X-ray gas around the red, which is where the radio emission is. This is a supermassive black hole. So the hot X-ray gas, though, is the site of star formation, or at least gases. As the gas cools, it can eventually become part of a star-forming region and form stars. And also, some of it will fall onto the supermassive black hole in the center and make it emit jets, etc., and winds. So the radio jets push aside the gas, as I explained earlier. It creates these cavities, and in this one, the radio emission fills the cavity. So you've got radioplasma shining in the cavity where there's no X-rays. The radio jets, in doing this, heat up this gas. So they stop it cooling, which slows down the star formation, because the gas needs to cool to form stars. Also, some of it, as I said, goes down to the core, and then the active galaxy has another outburst that heats it up again. So it's what we're calling a feedback loop, rather like the thermostat in your house. It starts cooling, the material falls in, then there's another outburst which heats it up again. Right? So star formation is slowed down, the supermassive black hole grows. So that feedback loop moderates both the stellar and the supermassive black hole growth. This one in particular is the largest continuous jet that we've seen. If you looked at the holes in the last one, it was clear that it hadn't been sending out plasma in the same direction all the time, whereas this one, the radio emission is filling this whole region. So it's continuously been a jet for a million. It's a million light years, so longer than that. This is another little movie that our communications people made, which shows what I just described. So here's the supermassive black hole. The red is the gas, and there we have the jets coming out, and they push away the gas, and they create these shock waves that just emanate out through the gas. And they do that over and over again. I'm now going to talk about dark matter. You've probably mostly heard about dark matter as well, by looking at another cluster, in this case, colliding clusters. It's called the bullet, for obvious reasons, because this looks a bit like the front of a bullet. This is actually two clusters that have moved through one another. Just to step back a minute, I've told you that the X-ray gas is 10 times more mass than the galaxies. But even adding all those together, we don't have anywhere near as much gravity to keep all those galaxies where they are. And we know that they're stuck. They can't get away. They're in a huge potential well due to gravity. So there has to be something else there. We can't see it, so we call it dark. It has to be matter because it's got gravity, so it's dark matter. We call it like it is in astronomy. No, Greek names or Latin names to confuse you. If the star's big and red, it's a red giant. So dark matter, we haven't seen it yet. However, we can see what it does. We can see the effect of the gravity. And that's what I'm showing you here. The galaxies in this cluster are shown in white, and also there's some stars in the field of view. The red here is the X-ray hot gas, and the blue is where we think the dark matter is. And the way we estimate that is by looking at the distortion that the gravitational force distorts the light. So when you think of the light coming through a lens in your glasses, the light is bent so that it can focus on the back of your eye, and your eye isn't working properly, right? So it changes the focus point. It bends the light. Gravity can also bend light. It has to be a lot of gravity, but it bends the light. So we can see, you can't see very well here, but you actually see these images of the galaxies being distorted and sort of bent. Sometimes you actually see a whole ring, but in this case, it's usually a distortion. And you can measure how much matter you needed, what gravitational force to create that shape. So that's how we got this estimate here of where the dark matter is and how much it was. So that's shown in blue. And so what's happening here, the interpretation is that as the clusters move through each other, the galaxies just keep going unless they come very close together, which very few of them will, because there's a lot of space between them, and they're pretty dense. So if you think of shooting a bullet through the air doesn't slow it down very quickly because it's much more dense and it's going very fast, and it can just go through the air. However, if you blow a smoke ring, maybe we have some smokers in the room, I'm not one, but if you blow a smoke ring, it slows down very quickly. It doesn't go very far because it interacts with the air atoms and it slows down. So what's happening is the galaxies have moved through. You can see they're concentrated here and here. And the gas has slowed down because it's got mixed up with the gas going the other direction. So you get this funny shape here. However, where's the dark matter? It kept going. We think the dark matter fills the space. So it should be seeing other dark matter particles coming the other way, but it's not interacting with them. So we know that these particles don't interact with one another from this observation. There's no drag on the dark matter. And we've seen this in a number of other clusters now. Actually, this is still the best one in terms of the separation. Of course, the more you look, the more complicated sources you see. This is a little movie that shows you the dark matter and the gas, not the stars, to show you what's happened. So they moved through each other, the dark matter's kept going, and the gas has slowed down, and that's the structure we saw. So even though we can't see dark matter, we can learn about it, which is pretty exciting. So that's the end of my science presentation. I'd like to introduce you to our astronauts. There were 5 astronauts on the Shuttle Columbia when it launched. We're still in touch with them. We talk with them every now and then, and they come and visit us on special occasions. And the last special occasion was in 2014, about 6 months after I became director. We had a big science symposium to celebrate 15 years, and 4 of the 5 came back. Eileen Collins here, the white trousers, was the commander. She was the first female commander of a shuttle. And Katie Coleman was the mission specialist for Chandra here. And then the other 2 astronauts is Steve Hawley, who actually has done quite a few Hubble service missions as well. He was originally an astrophysicist. And Michel Tognini, who is French, and he's from ESA. So he was on this mission. And then the pilot, Jeff Ashby, who was unable to attend this particular meeting. You can see all these beautiful Chandra images behind them. That, of course, was a big display we had at the meeting. We're having another meeting for 20 years in December in Boston, and so we've invited them back. Eileen has already said she can definitely come. I only invited them a few days ago, so I'm hoping to hear from the others. Jeff Ashby thinks he can come this time. This is a picture of them on the shuttle, looking a lot younger. And, of course, their hair's all up in the air. And there's a flag behind that says Chandra X-ray Center, which they brought back and presented to us. So we have it in our facility. in a frame, which is really neat. And then just to prove that I was there too, a picture of me. And finally, just a montage of Chandra pictures, some of which now you will recognize. The crab, Casset, NGC 1640. This is actually the galactic center, etc. So that's it, and I'd love to answer any questions.
Yeah, could you give us a sense of some of these distances? For instance, in the Orion constellation, in the star-forming region, in the dagger that you mentioned, how far apart are all these young stars that are interacting so furiously as to heat up all the area around them?
Yeah, it's probably mostly the material that's interacting rather than the stars. They'll be fairly far apart. I actually don't know the numbers, but it must be a number of light years, I would imagine, between the stars. But as they light up, they actually heat up the material around them too. So we also get emission coming from that.
But there's no interaction gravitationally among those stars?
Not usually. Usually what happens is you get the gravitational force, you get a perturbation, it's called, positive perturbation, where you've got more material, and because there's more gravity there, more comes in, and eventually your star forms. And then there might be another one nearby, and they do eventually turn in. There are binary systems that are planned, but they don't generally interact directly at that point. Not once they're stars.
What's your favorite Chandra image and why?
Can you repeat the question? Sorry, I missed that.
Yeah.
What's
Favorite Chandra image.
Chandra image and
What are your
why?
favorite Chandra images?
And why? Gosh. Actually, my favorite Chandra image at the moment is the one my student who's over there has worked on for the past several months, so my senior thesis. It's a 3C radio galaxy at a redshift about 1/2, so similar to the Parkes one I showed you. But it's actually also a gravitational lens. And so it has a sub-millimeter galaxy behind it at a redshift 2, so quite a bit further away. And the light is coming straight through this 3C galaxy in such a way that we actually see the whole ring. So if you have one source being gravitationally lensed by another one source rather than a big patch like in dark matter, you actually get what's called an Einstein ring, and the light just goes around symmetrically. And we see the Einstein ring in the optical with Hubble. It's just inside of the radio lobes. This is a radio lobe quasar, so it has radio lobes which are just sitting just outside the ring, which must be a coincidence. And we think we're also seeing X-rays from the ring as well. Somebody's been studying that for the last few months. So it's a really fun source, very pretty. I don't have a slide of it here, unfortunately. That's my favorite at the moment, but that might change. You might find another exciting one soon.
Question.
The orbit of the Chandra is fairly eccentric and passes into the delta, which prevents it from being open during the time. Why was that orbit selected?
So why was the orbit of Chandra chosen so that it matched the Van Allen?
Yeah. Oh, well, it was chosen to be elliptical so that we could look at a source for a long time, so we didn't get interrupted. The Hubble is basically in the shuttle orbit. It's only about 500 kilometers up, and it goes around every hour and a half. So for at least a third of that orbit, it can't observe because it's the other side of the source which you're trying to look at, right? So if the source goes behind the Earth, you can't observe it. Whereas we can actually sit for a day and look at the same source, or even 2 days, because it's a 3-day orbit, 63.5 hours, almost 3 days. And then there's only about 16, 17 hours while we're in radiation belts and we can't observe. So the idea was that we'd be able to look at things for a long time. And we needed to stay well outside the radiation belts for most of the time because the radiation damages our instruments. So that's why we closed down at that point. As time has gone by, we're actually not able to look at sources for that length of time because the thermal insulation in the satellite is degrading, and so we have to manage temperature very carefully. But we still observe the whole time. We just have to go from one source to the next. So it's very efficient. It's about 70% of the time we're observing sources.
Question, she's looking down now. Yeah, I think your hand went up first.
Two questions. Who was the Chandra X-ray named after? And how long will it live?
So yeah, who was Chandra named after, and how long will Chandra live? That's a good question.
Yeah. So Chandra was named after a very well-known Indian astronomer, at least in astronomical circles, called Chandras Orbit. He was Indian, but he lived in the US for a lot of his life. I don't know exactly how much. There's a tradition of naming satellites once they're launched after a dead scientist. So he conveniently died a couple of years before. But his wife came to launch. She was still alive then. I don't know if she is now. She came to launch. It was really neat. The name was chosen, though, through a public competition. We actually asked the public to suggest people. And Chandra was the one that won, got the most and the best proposals, if you like. I think it's great because I grew up learning astronomy in school, in university, from Chandra Orbit's textbooks. Very good one on stellar structure and another on radiated transfer. So anyone who's done astronomy in college, at least in my era, would have known his name very well. And he's called Chandra by his family, so that's why we shortened it. And in terms of lifetime, we have no expendables except fuel, and we have a lot of fuel. The orbit isn't going to decay anytime soon, so we're really limited by money. And as long as we're still doing good science, NASA should keep supporting us. At least we tell them so. We have a review every 3 years, which is going on right now. We have a panel coming in a few weeks. But they've been very supportive. We're unique. There's no other X-ray satellite that has this high resolution. So our sites would stop being done if Chandra went away. So we're hoping at least 10 more years. And there's always the possibility we'll get hit by the proverbial bus, which would be actually very small in space and could do damage. But so far, so good.
So time for 2 more questions. There's one person here and someone up there.
I mean, how much money did they cost for, like, sun? Sorry if I butchered the name.
Yeah. How much money did it cost to build it?
Yeah.
Build Chandra? About $1.5 billion at the time. It would be significantly more now, probably more like 3 if you inflated it. And then it costs about $55 million per year to run it. So a very small percentage of the building cost. Most of that is people, like Peter and myself.
Don't have any money right now. So there was a question up there.
Okay, so come on down when you...
Come on down. Let's do one more question. John.
Do we have like an intuitive explanation of why jets form or exist?
Yeah, well, we think that the magnetic fields form, they exist. And because you have a lot of material trying to fall in on the plane, the equatorial plane, the only way for the others to escape is sort of along the poles. That's the path of least resistance. So we think the magnetic field, because everything's very hot and ionized, just catches these ionized particles and they spiral around the magnetic field. And with all the studies that have been done of jets since we've been able to look at it and so much better in the last 10 or 20 years, there's quite detailed models now. Very relativistic flow and a helical, toroidal they call it, field that's winding around that spine, and the spine of very relativistic material, and then there's a sheath which is slightly less relativistic but still giving us the emission around that that's interacting with material around it. So similar to the description I gave of the gamma ray burst jet.
So I think that's it. You can please come down and talk to Belinda afterwards. You've got other pressing questions, including up there. And let's give her a round of applause.
Thank you again.